In 450 BC, a philosopher named Zeno proposed a problem that confused mathematicians for 2,000 years. Imagine you want to walk across a room. First, you must step to the halfway point. Then you step across half of the remaining distance, then half of that distance, and so on forever. You are asked to perform an infinite number of steps, yet you easily cross the room in a finite amount of time. How does an infinite sequence of actions ever finish? Let's look at the mathematical equivalent. Start with a line segment exactly 2 units long. Shade the first half, a length of 1. Now take the remaining half and shade its halfway point. Add a quarter, then an eighth, continuing infinitely. Notice what happens to the remaining empty space. Every single addition is filling exactly half of the remaining gap. The gap shrinks and the total grows, racing toward each other. After an infinite number of steps, every point on the segment is shaded. The total is exactly 2. An infinite sequence of additions perfectly resolves into a finite number. Visual intuition is helpful, but we can prove this exact result with algebra. Let's define this infinite sum as the equation S. Now, multiply that entire sum by a half to create a second stacked equation. Look at how the terms line up. What happens if you subtract the bottom equation from the top equation? The entire infinite tail perfectly cancels itself out. 1/2 minus 1/2 is 0. 1/4 minus 1/4 is 0 forever. You are left with s minus s over 2, which equals 1. Solve for s, and you get exactly 2. One simple subtraction collapses an infinite process into a single clean answer. We can generalize this specific trick into a universal formula. For any geometric series where each step multiplies by a fixed ratio r, the total sum equals the starting value a divided by 1 minus r. This gives us an absolute rule. As long as your multiplier r sits strictly between -1 and +1, the numbers will shrink fast enough, and the infinite series will always settle on a finite sum. This chart compares 2 different series. On the left, our geometric series flattens against a hard ceiling of 2. On the right is the harmonic series, 1 plus a half plus a third plus a quarter. The terms are getting smaller, approaching 0. It is perfectly logical to expect the bars on the right to eventually hit a ceiling too, but they don't. The total diverges. Slowly, agonizingly slowly, the harmonic series continues to grow and push upward. It never stops. We can prove why this happens by cleverly grouping the fractions. Look at 1/3 plus 1/4. Because 1/3 is larger than a quarter, their combined sum must be strictly greater than 2/4 or 1/2. Now group the next 4 fractions, a 5th, 6th, 7th, and 8th. Together, they are also greater than 1/2. As we continue down the line, we group fractions into larger and larger blocks, proving each block is always greater than 1/2. Because the series goes on forever, there are infinitely many of these blocks. If you add infinitely many halves together, your sum is infinite. You can add an endless sequence of fractions that individually approach 0, but if they do not shrink fast enough, the total will still explode. Calculating transcendental functions like sines or logarithms requires a bridge between geometry and arithmetic. Infinite series provide this bridge by defining complex values as sums of simple fractions, allowing a computer to reach any required degree of precision by simply adding more terms. Take the Taylor series for e to the power of x. It is built by adding powers of x divided by factorials. Because factorial denominators grow incredibly fast, the fractions shrink rapidly enough to guarantee convergence. And hiding within these series are profound connections. The Leibniz formula links simple odd fractions to the geometry of a circle. By alternating addition and subtraction, 1 minus a third plus a fifth minus a seventh, the sum oscillates before converging exactly on pi divided by 4. In calculus, we map these structural behaviors through convergence tests. Tools like the ratio test, comparison test, and integral test are designed to analyze exactly how fast a sequence shrinks, turning every infinite sum into a manageable limit problem. Infinity possesses a distinct mathematical structure. When the terms of a series shrink fast enough, the infinite sum sheds its paradoxical nature and resolves into a precise, fundamental constant of our universe.